Hello guys, in this video we shall be talking about multipole expansion, which is another way of calculating potentials at large distances and is a very interesting technique. So let's begin. So what is the main idea behind multipole expansion? So we express the potential at large distances as an infinite sum of potentials of decreasing order. So every term which comes after the previous one will have a lower order as compared to the first. So if any of the terms comes before another, then that term will be more dominant and that will more or less decide the nature of the charge distribution at a large distance or as seen from a large distance. So there is an assumption which is made, which is that charge distribution is localized over a very small region as compared to the distances we are interested in. And this aspect can be seen from this figure and while doing the derivation. So this is the first step, like how we can express the potential at a point in a general format. Here we'll use the cosine law and we'll be able to express the distance, and based on that we can actually apply the approximation that this capital R, not capital R, sorry, small r is much greater than r prime. So with that approximation, which can actually express it after a few steps using Taylor's series and all those kinds of tricks, we can actually express it as an infinite sum in some sense of these potentials. So we shall look at the first few terms because they are more relevant and more easy to understand. So the first term will have this sort of integral when L is equal to 0, and we can recognize this as the total charge in some sense. But we all call it as monopole moment, which is another word for charge. And associated with the monopole moment is the monopole potential term. And if this is not equal to 0, then we can say that at large distances, this charge distribution behaves like a charge in some sense, like a monopole. But let's say if this turns out to be 0, and what will happen then? Then we can resort to the next term, which will turn out to be the dipole moment, which interestingly is a vector quantity unlike monopole moment, which is a scalar quantity. So we can calculate the dipole moment, and if it is not 0, then we can say that the potential at large distances varies as 1 over r squared, and we can calculate the dipole potential term. And another note is that if the monopole moment is 0, then we can show that the dipole moment is independent of the choice of the origin. So we can take any origin and this vector integral will turn out to be the same. So these are some of the important first few terms. After these terms, we'll have quadrupole moments and octopole moments, but these are not really relevant for this course. Now we shall talk a little bit about dipole, although this has been covered during 12th standard, so this should be quite familiar to most of us. So these are few of the formulae that will be repeatedly used in many problems, such as calculating potential at large distances, which we have seen in the previous case is just 1 by 4 pi epsilon naught, the dipole moment dotted with the direction vector divided by r squared. So this is an important formula. An electric field can be obtained by taking the negative gradient of this, and we will get this in spherical coordinates. Based on that, we can find the torque because the net force in a uniform electric field will be 0, so we can calculate torque, which is not necessarily 0, by taking the cross product of the dipole moment and the electric field vector. And we can also find the potential energy in this similar manner by taking dot product of instead. Then in a non-constant electric field, we can define the potential energy in a very similar manner and find the force on the dipole by taking the negative gradient, because negative gradient of potential energy is the force due to that field. So these are some of the important formulae in this section on dipoles. So I hope this was helpful, and thank you.